Hello, in this video we will discuss about improper integrals. First, let me just give you what improper integrals are, some examples of them here. Here are a few examples of improper integrals. One is maybe from 1 to infinity of 1 over x squared dx, or another one from 0 to 1 of 1 over x dx. Well, what are these things? Well, we know when we're trying to find areas or other applications volumes, we calculate integrals. So we do calculate a function, an integral from a to b of f of x dx. Well, in this case, we do assume that the function f is defined all from a up to, on the interval from a to b, okay, all the way from a to b. And we assume that a and b are finite numbers. Okay, so we don't have infinity as one of the limits. So for example, we integrate from 0 to pi of sine of x dx or something like this. In this case, that really is from 0 to pi over 2. That is just the area from 0 up to pi over 2 of the sine function, under the sine function. So that's a proper integral, nice and fine, definite integral. But now we're dealing with integrals that have infinity as one end. Oh, well, why do we do that? Well, the idea is this. If you have, let's say, the function y equals 1 over x squared, y equals 1 over x squared, when x is 1, y is 1. When x is 2, y is 1/4. When x is 3, y is 1/9. So the graph approaches to 0 as x approaches to infinity. And someone might say, well, if you try to find the area, what does that approach to? Does it approach to a finite value? So then the question comes, how do we integrate? How do we find the area? We just somehow tend to integrate from 1 to infinity of 1 over x squared dx. So that's why this kind of questions come. And what makes this improper? Well, what makes this improper here is that we are integrating from 1 to infinity. Infinity is not a number. And this one is improper because we're integrating from 0 to 1. But what's the problem with that? Well, the problem with that is the function 1 over x is not defined when x is 0. Okay, when x is 0, 1 over x is undefined. So you're integrating a function where it's undefined. So here are some more examples, okay? Some examples here. I'll write these again from 1 to infinity of 1 over x squared dx, or from 0 to 1 of 1 over x dx, okay? Maybe from 0 to 1 of 1 over square root of x dx, okay? Maybe the integral from 0 to 2 of, let's say, x squared minus 1 over x minus 1 dx. What's the problem here? The function is defined at 0, it's defined at 2, but at 1, this is not defined. You get, if you stick 1 in for x, you'd be dividing by 0. So the function is undefined at 1, but we're trying to integrate it from 0 to 2. So that's what makes this an improper integral. On the other hand, this, let's say from 2 to 10 of x squared minus 1 over x minus 1 dx is a nice and proper integral. Yes, it's undefined at 1, but there is no 1 in my interval for the intervals from 1 to 10. So this is not an improper integral. This is a good integral, okay? This is a proper integral. So what makes an integral an improper integral is if the limit at the end is infinity, or it starts from minus infinity to some number, or from a to b, but there's a problem between a and b. The function is not defined. All right, so how do we do these integrals? So I'll just give you an example first, kind of like a recipe, and then we'll just do examples, okay? To evaluate the integral from 1 to infinity of, let's say, 1 over x squared dx. In other words, to evaluate the integral from a to infinity of a function f of x dx when f of x is defined all the way from a to infinity, okay, defined on this interval. This is a good prototype. Function at 1 over x squared is defined from 1 to infinity. How do we do that? Well, the first thing we do is we compute the proper integral from a to b of f of x dx. In other words, we change that infinity sign to some constant b, to some variable b, actually, to some variable b. Okay, in my example here, okay, I would compute the integral from 1 to infinity of, from 1 to b of 1 over x squared dx. Okay, that's what I compute. And then that will give me some expression of b. Okay, so I'll call it, I don't know, L of b. Okay, so this gives me an expression of b, depends on b. Then the next thing I do is I compute the limit of this new value that I got as b approach to infinity. The primary idea is this. So in the process of trying to find the area under this curve, okay, in the process of trying to find area under this curve, what we're doing is we're just putting a b here, kind of like a gap, a stop gap, and evaluate the area from 1 to b. That's a finite value, but it is a function, a finite value depending on b, so it's an expression of b. Once I get that, then I can push b to infinity. So by pushing b towards infinity, I am covering every inch of this region by taking the limit as b approach to infinity. Okay, so that's the idea. So now I compute this, and then I give my final result as if the limit, if this limit is finite, then I say that the improper integral converge to the limit. Let's say that this limit is, I don't know, L. So it converges to L. Otherwise, we say that the improper integral is divergent. So the limit could be infinity, the limit could be does not exist. So in that case, we say the improper integral is divergent. Okay, so in this situation, when it converges to L, okay, when the limit is finite, we write the integral from a to infinity of f of x dx equals L to mean the integral converges to L. Okay, it doesn't mean the integral, I mean, it's just an improper integral. So it does converge to L. That's what we write. So let's just have a quick example here. Okay, so let's compute the integral from 1 to infinity of 1 over x squared dx. Well, if we follow the recipe, we're going to change that to some value b and integrate this expression. Well, the antiderivative of 1 over x squared is minus 1 over x. So we evaluate that from 1 to b. This is just integrating 1 over x squared gives me minus 1 over x. So stick b in, minus, stick 1 in. Okay? So I put b, f of b minus f of a is what I'm doing, the usual antiderivative integral, definite integral. Well, this is minus 1, which means plus 1, minus 1 over b. So like I told you before, this is always a function of b. It's an expression of b. Okay? Usually, almost always is a function of b. Now, the second thing to do is compute the limit. As b approaches to infinity. Well, this is not a hard problem. It's not difficult. What happens to this expression when b goes to infinity? Well, if b gets larger and larger, let's say b was 10. If b is 10, this is 1 over 10. That's 0.1. Well, this has nothing to do with b, so it stays as 1. So I'm not worried about that number. I'm not worried about this one. I'm worried about 1 over b. All right, so if b is 100, this is 1 over 100. That's the small number. That's 0.01. When b gets larger and larger, this goes to 0. I know this is a Calculus 1 material, but some of you may have forgotten what that limit is. So that goes to 0, so this goes to 1 minus 0, which equals 1. Oh, okay, so a finite number. It goes to 1. And hence, the improper integral from 1 to infinity of 1 over x squared dx converges to 1. So that's my final answer. But I don't usually write it like this. It's just tradition. We don't write it like this. I'm going to scratch that out and say what I would write to mean this, okay? I'll simply write the integral from 1 to infinity of 1 over x squared dx equals 1. This says the same thing as that one, okay? Convention. So the improper integral converges to 1. Well, so I didn't give you the actual definition yet, okay? This is what the actual definition looks like, okay? So the integral from a to infinity of f of x dx, this improper integral, is defined as the limit from a to b of f of x dx as b approaches to infinity. That's what you will see in your books. And they usually put all of them all together and calculate. But I tend to break it into little pieces like this, okay? 1, 2, and then the result, okay? That's what I usually do. And I think I found that as beneficial. So I'm going to do some more examples, a couple more examples here, okay? The next example I want to do is the integral of 1 over x dx from 1 to infinity. So step 1, integrate from 1 to b of 1 over x dx. Well, what's the antiderivative of 1 over x? Everybody knows this. It's natural log of x from 1 to b. And now plug in b, plug in 1. Well, fortunately for me, this is 0. If you quickly to remind you what the natural log of function looks like. It's the inverse of the exponential function e to the x. It hits the x-axis at 1. So natural log of 1 is 0. And this is what y equals natural log of x looks like. Okay, so natural log of 1 is 0. So that's the first part. Next, I'm going to take the limit of the integral from 1 to b of 1 over x dx as b approaches to infinity. In other words, I'm going to take the limit of natural log of b as b approaches to infinity. Well, when b goes to infinity, natural log of b, as you can see it here in this graph, goes to infinity. It's very slow, but it goes to infinity. As b goes to infinity, natural log of b goes to infinity also, slowly. So this is infinity. What does that mean? That means that the integral from 1 to infinity of 1 over x dx is divergent. It diverges. Well, what did we get from here? What did we see? Well, here, if you see this example, the integral of 1 over x squared from 1 to infinity came out to be 1. Convergent, finite value, okay? Whereas this integral, seemingly the similar expression, almost the same, the graphs are almost the same, they look the same, this diverges. Well, what happens? Well, what happens here is this. If you draw the graph of y equals 1 over x squared, so 1 over 1 squared is 1, 1 over 2 squared is 1/4, 1 over 3 squared is 1/9. You're trying to find the area under the curve of y equals 1 over x squared. Sorry about that. Y equals 1 over x squared. You get 1. What it means is you need 1 unit of paint to paint this area under the graph of 1 over x squared. On the other hand, the graph of y equals 1 over x, 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is 1/3. It goes to 0 as x goes to infinity, but this region, because the function approaches to 0 very slowly, the area of this region is infinity. It's not a finite area. That's what this is saying. So the area under the graph of 1 over x from 1 to infinity is not a finite value, whereas the area under the graph of y equals 1 over x squared from 1 to infinity is finite. It's actually 1. Okay? So let me add one more example. This is example 2. I'm going to add one more example from 1 to infinity of 1 over x square root of x dx. Okay? In the next video, I will be doing 2 examples, very important examples. Okay? I'll be doing 2 very important examples, and these examples I will give you a quiz on those, exactly those problems, so gives you an incentive to watch those videos. All right, so this is actually the limit as b goes to infinity of the integral from 1 to b of 1 over square root of x dx. So let's calculate from 1 to b square root of x dx. This is from 1 to b of x to the minus 1/2 dx. Just change it to a power form so you can integrate. Okay, add 1 to minus 1/2 gives you 1/2. Divide by, so x to the power of 1/2 over 1/2 from 1 to b. Or 2 times the square root of x from 1 to b. This is 2 times square root of b minus 2 times square root of 1. Alright, this is 2 square root of b minus 2. So, the integral from 1 to b of 1 over square root of x dx would be the limit of this expression, 2 square root of b minus 2, as b goes to infinity. When b goes to infinity, this goes to infinity, square root of b goes to infinity. Because if you put, let's say, 100 in for b, square root of 100 is 10. If you put 1,000, then that square is bigger. As b gets larger and larger, square root of b also, kind of slowly, but goes to infinity. So this is infinity. It's infinity minus 2. All right? And hence, the improper integral from 1 to b of 1 over square root of x dx is divergent. No, from 1 to infinity. All right. I hope this helps, and I'll do 2 more examples on improper integrals. All right. Take care.